Welcome to the panel discussion on innovations in quantum sensing. In some sense, if you look at the constitution of this panel, it's like a litmus test on how fast or how much this field of quantum science and technology has moved forward. If we had a panel like this 10 years ago, there would most likely be 3 physicists. And if they were feeling kind on that day, they might include a chemist. Today, we have a physicist, we have an electrical engineer, and we have a product development leader with a business background. So let me briefly introduce them, and I'll request each of them to give a short, maybe 5-minute description of what they're working on, what's exciting to them. And after that, we'll open it up to just a panel discussion. I'd love to keep it informal. I'll ask some questions. I'd encourage you to ask a lot of questions, and I'll shut up if you ask good questions. But let's get started. So on my extreme left is Luca Ferrara. He is General Manager of Navigation in Sandbox. He oversees the development of Sandbox's magnetic quantum-based navigation systems, which will hopefully be an alternative to our conventional GPS. Before joining Sandbox, Luca was a product manager at X, which is Google's moonshot factory. And over there, Luca led several transformative projects in the area of artificial intelligence. And prior to that, he was an associate lead at Google's cloud sales strategy and planning group. Now, Luca has a background in financial services, and he also holds an MBA from the Booth School at the University of Chicago. So welcome back, sort of like to Chicago again, Luca. Next to Luca is Professor Jennifer Choy. Professor Choy is professor at the Department of Electrical and Computer Engineering at University of Wisconsin-Madison, where she leads a group conducting research on quantum magnetometry, focusing on neutral atoms as well as color centers in diamond. She has her own startup, she was the founding scientific advisor for Dirac Labs, where they develop quantum sensors and algorithms also for magnetic navigation. And prior to joining academia, she was at the Draper Labs, and she holds a PhD from Harvard University. And right next to me is Professor Dana Anderson, Chief Technology Officer of Inflection. He's also a professor of physics at the University of Colorado Boulder. And Dana is an applied physicist with a lot of extensive experience in quantum optics as well as precision measurement using quantum technology, optical neural networks, signal processing, and quantum systems based on cold and ultra-cold atoms. Great. So with that, I'll request Jennifer to kick it off. And because of this very multidisciplinary audience we have, we've requested Jennifer also to give you guys like a very short primer on quantum sensing.
Thank you very much, Supratik, for the introduction. Everyone hear me okay? Great, thanks. And I'll look at my my phone so I keep track of the time. So yeah, I was asked to talk briefly about what quantum sensing is, and I think at its core, to me, quantum sensing is basically using discrete observables in quantum systems, and that can be from energy levels in atoms. It can be of basically nuclear and electron spins in both real and artificial atoms, and as well as discrete, flux or charge from superconducting qubits. These are discrete observables that are sensitive to the environment around it. And if you have a good way to actually measure changes in these discrete variables, for example, by monitoring changes in resonant frequencies and in atoms, then you actually have a good sensor that basically transduces the signals around the sensor itself into an observable signal. And you know, a couple of more specific examples is so the field of quantum sensing is very close to the field of metrology, the science of measurement. So if you have a really good physical understanding of how an atomic system, for example, again, looking at electronic energies in atoms that are isolated, well isolated in, for example, the vacuum cells that I know Dana brought that he's going to show later. If we have a good way of monitoring changes in those electronic energies and then map that to a physical understanding through, you know, if you solve the Hamiltonian of how that quantum system interacts with this environment, then you actually have come up with a really precise and accurate way of measuring a particular signal, but also just coming up with new ways to define time and frequency. And you know, one of the things that quantum sensing has already impacted our world is through the atomic clock. Currently, we all rely on GPS, that, you know, our phone is telling us where we are, and that's inherently from triangulation of GPS signals, but then GPS satellites have an atomic clock on board, and actually more than one, just for redundancy. And really is the broadcasting of, in addition to position, timing information that basically enables the accuracy of GPS. So really one big advantage of basically using anything quantum for sensing is the ability to really set standards like this. You're relying on the inherent stability of quantum systems. You're reliant on well understood ways that these quantum systems interact with the environment, and they also interact very sensitively, so you get very sensitive measurements too. And applications like, you know, being able to tell time more accurately and precisely with atomic and optical clocks are enabling, you know, us being able to navigate. They are important for data communications, like basically all the data towers, cell towers, financial centers require having a very well-known and well-referenced timestamp. And we're also building sensors to basically improve our ability to map magnetic fields, and then we're going to talk about applications of that later in this panel with Luca's work. And so that there's myriad of applications, and is already kind of bringing us some benefits in real life. And I do want to bring up another flavor of quantum sensing that's sometimes used in conjunction with this simple idea of being able to do measurements of discrete observables and discrete degrees of freedom in quantum systems. And that's leveraging concepts of coherence, which, you know, quantum systems, in order for them to remain sensitive to a signal, need to remain coherent over a long period of time, meaning that it's quantum states, it's being maintained over long periods of time. But then there's also the concept of entanglement. And there actually an exemplar, I was just talking to Dana right before this panel, and an exemplar application of where there's a very clear advantage to being able to leverage entangled quantum states. It's basically the LIGO experiment, which is being used to sensitively detect gravitational waves. And there, primarily, the experiment itself is based on interfering light waves and being able to measure very, very small phase changes due to the effect of gravity on the mirror components. And there, the limit is, you know, quantum sensors also have a limit, and that limit typically is set by basically discrete nature of photons that are hitting detector. And by leveraging entanglement, and in particular squeeze states of light, where you're trading off different properties in characterizing light waves, trading off noise and one property into so that you get a more precise definition of others, you have actually achieved record levels of sensitivity in this interferometer, which is enabling gravity wave detection. So I think these are some of the concepts that are going to come up in this panel. And for my work, very briefly, because I'm taking too much time, my work is very much about engineering quantum sensors including cold atom sensors, including artificial atoms in the solid state, and using that for nanoscale measurements. Basically trying to engineering that so that they're suitable to be operated outside the lab so that we can explore applications in GPS-denied navigation. I'm also working with some scientists on campus to basically build new types of fusion diagnostics using quantum systems, and also various applications, including semiconductor metrology. So I'll hand it over to the other panelists to talk about their work.
Great. Why don't we go to maybe Luca, and then we'll go to Dana.
Sure, thank you. So where we fit at SandboxAQ, and specifically with our AQ Nav group, is almost we're at the jumping off point from where your work kind of ends in some ways. Insofar as we want to focus on applications of the quantum sensor, and the reason why somebody like me, who has a product background, has entered into the space is because we're now at the regime where you really need to understand the user's journey, their pain points, and et cetera, such that you can give them a value proposition and have product market fit in such a way that the quantum advantage ends up being something that's economically valuable and is recognized by your user and is something useful. So in our case, that's using magnetic sensors to do a very simple job, which is to detect Earth's magnetic field, specifically so that we can do map-based comparisons. The interesting thing is that the map data that we use is globally available. It can't be jammed. It can't be spoofed. It's all weather, and it's all domain. You passively sense it with these magnetic sensors, and you can store the data locally. These are advantages to this positioning modality in concept that if you get the engineering right, you can translate into a capability. That's a capability that increasingly in the 5 years that I've been focused on this has become more and more urgent. So when I first, and we first got into this space talking about alternative PNT, I think many people in this room and in quantum recognized that this was an application area for quantum sensing. My experience and our experience has been that we get a lot of inbound about the issues of GPS denial and jamming, everything that's so useful about it, and it is a case study for quantum. In a way, because of the atomic clocks. The utility of GPS is its weak point. And so that's the problem statement. GPS jamming and spoofing has increased by multiples over the past 5 years, largely due to geopolitical factors, both friendly and foe in a way. It's become the modus operandi of pretty much every state actor to jam and deny GPS in conflict zones. And that bleeds over into civilian airspace. And it is incorporated into the strategies of the DoD, which you can read yourself. So where we fit is in the procurement of commercially available magnetometers, and 95 cents of every dollar that Sandbox spends in development is on the software related to those sensors, meaning signal processing such that we can get a clean signal even in situations which the sensors are doing their job, but there is legitimately other confounders that are not Earth's magnetic field. And then designing proprietary algorithms such that we can do navigation with that signal. And that's why we have geophysicists on staff as well as navigation engineers. From our users don't care particularly about how we accomplish that. Quantum advantage for us is that we have a device which allows us to do magnetic anomaly-based navigation. So there is no prior classical magnetic anomaly-based navigation. So when we talk about quantum advantage and when I convey it, it's about more of a binary state, which is that prior to the availability of these sensors, you didn't have the base data, the substrate, for any of the application-specific software to do its job for this particular application. So it's the bias stability and the accuracy and sensitivity of these, but particularly the fact that the accuracy and the bias stability, which is so important for certain of these sensors. So for our use case, rather than exquisite sensitivity. So that is all our interest point. We have expertise inside of Sandbox for the development of magnetometry, but we also largely are focused on working with academia and commercial suppliers to us that might be connected to academia not so long ago, such that we can do something that's useful to our users in the PNT space. And so we have projects mainly in the aerospace domain with the Air Force. We've done work with another CQE member, Boeing, A Cubed, which is an Airbus Silicon Valley accelerator, NATO Diana, and the Royal Air Force as well. So there's more to come, but we're really excited about what we're seeing and being able to deliver quantum advantage. We have over 500 flight hours with quantum sensors, some of which were very air sickness inducing for myself, by the way. So I've actually suffered quite a bit personally to get these sensors out there. So I can tell more about that later, but yeah, so that's enough for me.
Okay, thank you. Dana?
It's a pleasure, by the way, for me to be back in Chicago. I grew up here in Hyde Park. Does this work better? Grew up in Hyde Park, so as I said, it's a pleasure to be back. So I am the founder of a company called Inflection, originally called Cold Quanta. We were founded in 2007. We thought quantum would become useful in 2 or 3 years, and here we are 19 years later, almost. Inflection was born out of science at the University of Colorado. The first time that researchers, my colleagues there, also at Harvard, excuse me, MIT at the time, cooled atoms using laser beams and other techniques to very close to absolute zero, where they form a quantum state. And that achievement of what was called Bose-Einstein condensate revolutionized physics in many ways. I'm an applied physicist, and so my thinking at the time was, well, this is going to be very useful. And that ultimately led, thanks to DARPA and other DoD funding at the time, that led to the founding of Cold Quanta, where we thought we'd get this technology out to everybody and it would become useful. It's taken a little longer, 30 years, but now the utility is become pretty apparent. And I wanted to complement what you already heard from Jennifer about the utility of quantum technology. In our case, it's based on atoms. You can use the internal states of atoms, what the electrons are doing, to make very precise measurements. You can also use the center of mass motion of atoms to make measurements. And it's still unbelievable to me, even though we do this routinely, that you can take an atom and you can split its wave function. It can be 2 places at once. And using that 2 places at once and bringing it back together can give you an extremely precise measurement of things like acceleration, rotation, and thanks to Einstein, also, for example, for gravity. So one thing I want to tell you that's already coming to be useful in a short amount of time is Inflection is working on an instrument in collaboration with a NASA mission. It's called the Quantum Gravity Gradiometer Pathfinder, to have a gravity gradiometer in space. It measures the Earth gravity. You'd think we know what it is by now. You measure the Earth gravity, but it actually changes a bit when the water melts from the polar ice caps or evaporates from some region of the desert or arid area. So you can measure changes in the water table and the ice around the world, and that's very useful to know where there's the impact of drought, et cetera, and so on. So that's in the short term. Inflection has also had cold atoms aboard the International Space Station since 2018. I wanted to give you just a view, and you're far away, so you won't get a very good view, but this is a complete core part of the system that was intended to measure rotation and acceleration. It's about this big. It's made of silicon and glass. It has a vacuum pump. And really key is when we cool these atoms with laser beams, the system itself is at room temperature, just as you see it here. It's the laser beams, very unintuitively, that cool the atoms. So it is remarkable what you can do with quantum sensing. I wanted to give you some concrete notions of sensing what. Jennifer told you about clocks. Inflection and many other people have atomic clocks already as a product. They've been products for quite some time. Inertial sensing, doing similar things to try to relieve the vulnerability of GPS, especially in conflicted times. You can make acceleration, rotation. You can know where you are by making inertial measurements. Likewise, we use the internal states of atoms to measure radio frequencies. So you can replace an antenna with a cloud of atoms and get very sensitive detection of radio frequency information. And that has specific uses. I won't go into it unless somebody asks. Specific uses which are different than what you can get when you use a standard electronic system beginning with an antenna to receive very weak signals. Maybe I'll pause there and we can get on to other more general questions.
Sure. Yeah. Thank you. Thanks for introducing, and thanks for keeping in time and yet being very informative. I'll kick this off with a question, and then we'll go to the audience and we'll go back and forth. So there comes a time when a technology makes itself known by creating a product that for the public that is a commercial product that people buy. Sometimes it's a major product and sometimes it's a smaller product, An example is CMOS. We all use CMOS in our computers, but one of the first applications in the 70s was its use in wristwatches, electronic wristwatches. I think Timex used it. So what do you feel would be this specific product impact in quantum sensing, the first one? And maybe we start with Dana and go down.
Well, I think we'd agree that the first product is already out, and that's an atomic clock. And you mentioned Timex. It's unbelievable. You'd say, well, why do I need to know the time any better? It's going to end. This meeting will end in 20 minutes or so whatsoever. The value of knowing time to many significant digits is entirely unreasonable. How valuable that is. For example, you want very good timekeeping for the electric grid. You want very good timekeeping so that when you or your stockbroker makes a trade, that we know exactly that you made the trade before this other person made the trade, and so on. The timing resolution you need to do that is incredible, and also timing, and particularly time syncing, plays a very key role in secure communications. And so there are two things to note. One, the incredible value of time. It's already out. Second of all, there's no better indicator of the headroom of quantum than looking at time. Today's laboratory quantum clocks are 1 million times more precise than the timekeepers at NIST that are used to disseminate time in the US. 1 million times, not a factor of 50%, not a factor of 2, 1 million times. That's how much headroom quantum clocks have to go to advance where modern technology is based on quantum today.
Yeah, I think Dana gave the best example in atomic clocks. So I will actually offer another example, which is the use of atoms to measure magnetic fields, basically magnetometers. And that actually uses a very similar principle as how you would make an atomic clock, which is, in this case, you're going to put atoms in a vacuum cell, similar to the one that Dana was showing, and then you're going to measure it with lasers. And so because this type of technology shares the kind of core component, enabling component that's needed to put together clocks that you can take outside of the lab, that actually has a great potential to also impact many different sectors. And among some of them include basically measuring biomagnetic fields. Our body generates magnetic signature through firing of neurons, and the fact that we can use quantum systems. And here, in addition to just using atoms, we can use artificial atoms, which are basically kind of analogs of these trapped atoms, but then kind of stuck in a crystal. And you can actually make really sensitive measurements of magnetic fields that way. And one application is to basically use that to basically measure biological processes. Another one would be Luca's application of basically leveraging not just the sensitivity, but the fact that quantum sensors tend to have really good accuracy if you really do all the work that's needed behind the scenes to really isolate the quantum system so that its unwanted signal is not affecting its performance. once it's really reliable and accurate, then you can use it for applications like measuring magnetic anomalies. And so I would say that's another kind of application that where a lot of the enabling components are already there and ready to really push these sensors out of that. They have been out of the lab, and then we're getting to the point where we don't even think about what quantum sensor is being used for a particular application. And I think that's a kind of that going with that CMOS analogy. That's sort of where we want to be.
Yeah, I would tend to agree with Jennifer, of course, selfishly. But I would go broader than that and say the quantum applications in PNT are going to end up being used by end users as a fusion of sources. I think that individual companies may develop particular technologies and refine those, but if you look at most vehicles, they have a variety of different sensor modalities on board for redundancy. And indeed, the value of quantum really is not to replace GPS, it's to be a complement or a supplement redundant system. So in my view, what will probably be the home run for quantum is when there are autonomous systems on the road or in the sky that are using the confluence of several of these systems to achieve things that simply were not possible before. So when we start to see planes being able to fly without pilots or helicopters in large numbers, or IoT being extremely fine-grained in terms of the positional awareness of where things are, allowing better understanding and analytics and better autonomy, perhaps robotics as the cost goes down. So I think that the quantum, we use GPS time, but most people are not aware that the time service they're getting is from the satellite. They just know that they have, most consumers just know that they have a signal from GPS. And so that in it of itself is the confluence of many technologies as well, including a user interface like Google Maps that actually makes that actionable information. So when does it become actionable? I think when it's all incorporated into something related to autonomy. I think that's when people will say we were not doing that before. Thanks to quantum technologies, we are, and it's something I can see and experience. And I think that's not far away.
And what do you feel is the main technical risk factor that's in the way, if you feel there is any, in terms of this turning into a reality that many people are going to use? It's going to be scalable, commercial, etc.
I think there's a mix of things. On the technical side, where companies like us have been investing, and if you look at the types of people we've hired over the last 2 years at Sandbox and our AQNav group versus the first 2 years. First 2 years, more physicists. Now, aerospace engineers. Why do we do that? Because our technical risk is really around ensuring that when we deliver a solution, it's up to the standards of the industry that our users expecting. So I think some of the technical risks are actually on the implementation level and may no longer have to do with because some of these things have been handled. Right? So we're standing on the shoulder of giants in that way, and our work is to deal with some of these integration issues.
Yeah, I think maybe following up on that, I completely agree. But the one technical challenge would then be, quantum states are by themselves can be fragile, and we're kind of using that fragility and their sensitivity to the environment to measure magnetic fields, measure pressure, temperature, whatnot. But then that sensitivity also makes it kind of a problem if you are trying to operate in a real-world scenario. And here's where some of the engineering and integration work comes in, is to basically protect the quantum sensor itself from unwanted signals that affect its operation, which can include temperature and pressure changes. If you're talking about flying quantum sensors, it can definitely include vibrations, and basically being able to both design ways to build that quantum sensor that inherently protects it and makes it robust, and then also with all the components that go with it, basically figuring out ways to integrate them better so that you're less sensitive to the unwanted environmental perturbations, so you will. And I think actually a key part of that is something that Luca talked about, which is the concept of sensor fusion. There is likely not a single quantum technology that works for all types of sensing, and also not a single classical or quantum technology that works for everything. And I think it's by merging many different types of sensors and having them look at the same signal, but maybe at different times, and be able to kind of fuse that data together, you actually are making a more robust sensing system overall.
Dana, would you like to add to that in
Sure.
terms of risk?
It's interesting. There's when you say technical risk, what I'd say is the physics of most of what we're doing with, first of all, is well understood. And I would say there are engineering challenges, but the real risk to me is less technical and more about a barrier I call the price-performance barrier, of getting something which is competitive with other techniques, because nobody cares if something is quantum in the end. They just wanted to do what they needed to do. But since we're doing the first ever of X and Y, it tends to cost a whole lot. And so I view there are technical risks. There aren't that many, let's call them unknown unknowns. But you have to keep at it through this price-performance barrier with patience of investors or investment from the government and so on. I view that as the challenges facing startups, facing quantum technology as a whole, of being able to pierce that price-performance barrier, making it cheap enough, soon enough, so that you can actually penetrate a market. For example, I don't think there's much technical risk in even in quantum computing much anymore, but there certainly are substantial engineering challenges. With sensors, it's another scale down, it's easier, but we still have to penetrate this challenge of getting there soon enough at low enough cost.
Let's take a few questions from the audience.
Yeah, thank you for sharing your perspectives on sensing. This is very interesting stuff. My question is around processing of the sensed data, right? So for the most part, I mean, the examples that you've given look like processing is happening exactly where you're sensing. But do you anticipate scenarios where you need to decouple where the processing is happening and where the sensing is happening, and potentially even fuse data from multiple sensors, and what kind of fidelities and what type of infrastructure support do you need to actually bring all this data to maybe a quantum data center or a quantum, processor somewhere, I don't know, miles apart from where the sensing is happening?
Yes, is okay? It's a super great question, and you really point to two things. The first is the fact that actually in quantum, you can gain enormously by distributing sensing. You can get much more information if you have a sensor over there, over there, over there, but of course somewhere you have to collect it and process it, number one. Number two is absolutely fascinating that you've got quantum data. The moment you read it out with a detector or get it into a computer, it's no longer quantum. It's extremely interesting, as I talked about headroom for quantum. Part of the headroom is, well, we would like to start processing that data while it's still quantum. And there could be an enormous advantage of that. That's further downstream. We will probably wait at least for small quantum processors and so on to be able to connect with the quantum sensors. And finally is the combination of the two. There, the quantum network, the quantum computing people are way ahead in thinking about how do I now distribute data, keeping it as quantum form, processing in quantum. That's the whole kit and caboodle. So I think that's on the horizon. Incredibly interesting questions. And today we are mostly talking about single point or modest distribution of sensors. After all, LIGO is a distributed sensor, right? I think you'll see more and more of that as time evolves. Jennifer? Yeah.
Great. Angus, we've got one in the back from our Zoom feed, correct?
So there's a question from Brett Porter. Is it realistic to expect quantum sensors and drones in the next 5 years if the drone market continues to grow?
I think it's very realistic. I would handicap that at a very high rate. It really depends on what size drone, commercial drone, the economics are unlikely to work out in the near term. But something class 3 and up, I think, is a very reasonable assumption to make much earlier than 5 years.
Agreed. There actually have been a bit of quantum technology on drones, kind of one-offs, just to demonstrate it rather than really being, on the way to a product. But I don't think there's much of an issue. And I'll remind you that I think you heard about the how many times 500 flight hours, 700 flight hours. Likewise, Inflection has been on boats, planes, automobiles, and what am I missing? Boats, satellites. So the environment robustness is already there. I just think it's a matter of time.
Hey there, Connor Feuiger. I'm a quantum systems engineer with QuantCAD based in Hyde Park. Mine is a little bit of a tangential question, but maybe then I can steer it on track at the end. As a Chicago native and an experimentalist who's worked on neutral atom systems before, I'm very excited to hear that Inflection will be coming to the IQMP. And I was wondering if you could talk a little bit to those efforts, what operations you're planning to bring there. Is it only going to be the information platform or also sensing, assembly and manufacturing? And then also maybe to the other panelists, just what do you see your sensing efforts, interactions with the IQMP and the manufacturing facilities there?
Sounds like something pretty directed to an Inflection. Well, we're very excited about planting our feet deeper in Chicago. As some of you know, we have we acquired Supratik some time ago. They're a quantum software company. Inflection not only does sensing, it also builds a quantum computer, which we're putting in the IQMP. But furthermore, we've committed to developing some sensor technology, particularly related to what I mentioned about using atoms to detect RF. That's a very new capability that's drawn a lot of interest, and we intend to do some of the manufacturing here. And also, I will tell you, for anybody who's done something complicated, it takes an awful lot of systems engineering, a different kind of, it's not sitting in your lab and doing soldering and so on. It's a whole system that we'll be deploying, and that we hope to cultivate quite a bit as we plant our feet in IQMP. I hope that partly answers the question. There might be some of our Chicago colleagues here that can add to that, especially on the quantum computing side. But we're very excited.
You guys want to add anything about your involvement in IQMP? Otherwise, we go to the next one.
Maybe a very brief comment about how I primarily do. I'm based at Madison, and I do research with the university, and I have more recently been this scientific advisor for Dirac Labs, which very much it's Madison-based startup that benefits a lot from being part of the Midwest quantum ecosystem, including Chicago Quantum Exchange, and Sanket, the founder, of many conversations with Tate Timmerman about how to best leverage resources. And then also with the IQMP, one of the main strengths is sort of workforce development, being able to both have potential jobs that for students that I train, but then also training people for the specific efforts, including integrating quantum sensors. It's just one example.
Tim?
Testing. There we go. So kind of a fun question for you guys. I read some time ago that our sense of smell is quantum-based. I don't care to understand, or I want to understand, but probably never will understand why that's the case. But I'm curious, what do you think the odds are we'll have some type of quantum nose, in the future? Now, I know we have radon detectors and helium detectors and that type of stuff, but I just want a detector, right? I just want to know that that's PTFE and that's chlorophyll, and you know what I mean? Like that's kind of what I'm interested in. So I'm just curious where you think we'll go with the sensing, and is this something in the future will hold for us? So
do any of you see a quantum nose on the horizon?
I have to laugh. I had before Cold Quanta, I had a company involved in the company called Alpha Sniffer, and it was exactly for nose, and we invented something where I affectionately call the sniff lock loop to try to identify chemicals. I think it was a little bit quantum, not very quantum, but I think the processing ultimately of smells is probably something that matches, in fact, very well as long as you get the data into a computer to actually do the smelling. The one other thing I'll mention is there's a company that came out of Colorado called LongPath that uses, it's called quantum technology, it uses laser beams. It uses something called the frequency comb to measure the amount of methane in the atmosphere at a distance. And they have something like $250 million sort of loan from the government to cultivate this technology to address, methane smells. It's not, I wouldn't call it a nose that they're doing. It's spectroscopy. But you see these things coming a little bit on the left and a little bit on the right, so I won't be shocked.
Let me ask a question here, and maybe I'll start with you, Jennifer. Do you feel we are paying enough attention to foreign competition in quantum from a competitive point of view?
I guess from my perspective, I have to pay attention to it because it's going to conferences. That's a good way to learn about what everyone is doing. And also, it actually is the start of many collaborations. I don't just collaborate with people in the US, I collaborate also with yesterday, I actually was what is that event celebrating the U.S.-UK prosperity deal. Just over the summer, I invited a scientist over from the University of Strathclyde to basically work together on how to better integrate our cold atom traps so that when we're building an inertial sensor out of these cold atoms, they're going to be more smaller, more compact, and work better, for example, with these compact cells that Inflection is making. And so then I see that I see international collaborations as super important. And I think within academia, we have to pay a fair amount of attention anyway, just because we have to be aware of what everyone is doing to learn, but also just to how to set our own metrics, or what is success for us. But yeah, I think we do.
Okay, your thoughts? Do you think as a community we're watching carefully what everyone's doing?
I think there's certain people I've met who are certainly worried and seem to be taking the appropriate caution. I think it depends on a particular individual's perspective. I think as a community, on balance, things are. My perspective is that things have been open enough. I think that there's good collaborations that I've had with folks in the UK, Canada, in Europe as well. As far as other regions, I think that there's a little bit of opacity that we all have to deal with in terms of understanding exactly how things are developing. We don't have competing products in certain markets, but it's also because we don't know what we don't know. So we try our best to be informed, but I wouldn't say that there's always unknown unknowns, of course, but at the moment I don't feel there's a major adjustment needed.
Dana, your thoughts?
Well, first of all, internationally, I would say I'm extremely proud to be working very closely with across the ocean in the UK. We have some of our UK colleagues here, in Australia, and in Japan. And I'm very proud, in fact, of the collaboration because we all ultimately have the same mission. There is competition from, especially you've heard about GPS, the worry about jamming, spoofing, denial, and so on. And we are all pointed towards the fact that we live perhaps in a delicate world occasionally. So let me also agree with Luca that things are a bit opaque with the serious competition. The rest of the competition I view, we compete with each other, right? And that's quite okay. We collaborate on the right side. There's competition that's much fuzzier. But I will tell you, for example, China is considerably ahead of us in putting quantum in space. And we know how hard that is and how long that takes. It's not exactly clear what our competition is doing, but they're clearly very active. And so do we pay enough? I'm not sure, but it certainly is. We have our antennas and radar up, trying to pay attention.
Let's take some more questions from
Gregory,
the
I
audience.
think we've got another question from our Zoom audience, correct?
Yes, indeed. On Zoom, we have a question from April Welch. April asks, what should engineering students be focusing on to make contributions to research in quantum sensing?
You can start.
Sure. Yeah. Maybe I'll bring like an example from when I was in industry at Draper Lab, working on a quantum sensing project. It was funded by DARPA. I was working with probably a team of upwards of 10, 15 people that a lot of them are just electrical engineers, mechanical engineers. We always need people to generate like good CAD models for building our sensors, and then also doing all the modeling of like thermomechanical effects of what happens when you're, for example, shaking the sensor, right? So all those analyses are crucial. We need great electrical engineers, per the point earlier about, okay, what is needed in terms of computing for sensors, and that can be actually quite complex because you're sometimes computing locally, and then also you need to distribute the signal, right? So we need good electrical and RF engineers and software developers. And then that team didn't really have a lot of physicists. And really it's when putting together any system, any products, right, it actually requires a big team of engineers. So I think actually that in terms of, the question was about what, can students do, I think basically go with things that they're interested in. And then I think the other maybe piece of advice is I actually think it's really immeasurably beneficial to actually have practical experience, so including, for example, industry internships.
Hi, thanks for all your perspectives. I have a technology-specific question. I'm sorry if it's too specific. I'm just curious your perspectives on where thorium is going to fit into the sensing architecture. Based sensors.
Yep.
Yeah.
So it's a great question. So for those of you, the rest of you, the interest in thorium, at least I'm assuming you mean with respect to timekeeping, is there is a nuclear transition, a little bit like an electronic transition in an atom with the electrons going around, but a nuclear transition that can be excited, let's say, with laser beams. And so there's potential of extraordinarily still more accurate clocks and clock technology. What I find so interesting, here's my answer. Back when we were thinking about cold quantum in 2005, we thought we'd have technology out in 5 years and we'd be done. And of all the technologies, in some ways, with all deference to them, clocks are the stupidest, easiest thing you can think of doing, right? And it still took 30 years. So I think thorium has probably a role to play, but it's going to be a very long haul to get it to be turned into a product. With all the acceleration the government's putting in, it might cut 30 years down to 10, maybe, if we work real hard at it. But it's hard. But it's very exciting. And so, again, unbelievably, another factor of 10, 100,000 in improvement if we can make a thorium clock. Did I answer your question?
Hi, Dimitris Konra. I'm a physician scientist at the University of Chicago. So you mentioned biological processes for the sensing. So I want to ask what biological processes you can use quantum sensing to measure now, and what you think is potential in the future.
You're referring specifically for medicine, biology and medicine? But yeah, so I guess the primary example, the one that basically really leverages the fact that with quantum magnetometers, you can get to kind of femtotesla, basically 10 to the minus 15 femtotesla level times 1 Tesla level of field sensitivity, really allows you to basically probe small electric fields emanating, let's say, from the brain. And that's actually an application known as magnetoencephalography, and that primarily requires really exquisite magnetometers that in some cases superconducting systems. But the advantage of atomic magnetometers is that it requires only a vapor cell, and sometimes you can actually miniaturize vapor cells and make a network of them, and that actually is a really great potential solution for doing this measurement that requires that sensitivity. There are other applications, including basically measuring fetal heart rates, and that is along that principle. And that's mostly about like, okay, can you put diagnostics on the body? But then there are also I see a lot of actually researchers in this room from Argonne National Lab working on making the best possible quantum sensors using these color centers in diamond. So diamond is a biocompatible material. So if you can make sensitive magnetometers that are inherently kind of atomic scale, you can imagine crushing up that diamond and then putting that inside cells to basically study cellular processes. So there's various scales of this.
Really enjoyed the talks. So how do you, or how would you like to be able to find people with potential applications for your sensors? That's really, in a way, a market question. How do you find these people? Or if you have an idea, how do they find you?
Actually, yeah, we can show Luca. Start with Luca.
Yeah, I think depending, the way I see the areas that Sandbox is focused on, we believe that there is a large unmet need that we've done our own diligence on. And we have a thesis that the technology is bridging a solution space and a problem space. If we're right about that, we should have a fair amount of inbound interest about the application area. If we're wrong about that, we're going to be knocking on a lot of doors without many people answering. And so when it comes to PNT as an example, I think we can say that this is an area in which across the stack, most companies that are focused on some version of an alternative PNT technology, be it classical, software only, or quantum, they're getting a tremendous amount of inbound interest from people who've been given a mandate to go find a solution, because the problem is real. And that's the critical thing, is that it's not an imagined problem. There's a lot of data to back it up. So that's one case. I think where I'm going to go a little bit more into like just my opinion, like purely is about, in speculating about the future, would be that in areas in which quantum is going to allow us to do things where we could not before, such as the application that you mentioned, I think that's going to require a little bit more nuance in terms of finding somebody, the right stakeholder who can lean over the table with you, take a bit of the technical risk, but incentives are aligned such that they know what they're getting into. You have the right feedback loop around your application, and you can make measured progress, keeping expectations aligned, right? That's a really hard match to happen. I wish I could give you an answer about how that happens really well. I think you show up to conferences like this and you hope. Do you have a website? You have a nice LinkedIn photo? I don't know. But yeah, I mean, I would take advice from anybody about how to do that best.
Now, this is actually an extremely important question, because quantum can do things, so we know from the, those of us who are doing it say, boy, it's got to be a great solution. I'm just not sure of the problem. And that's what happened to lasers for years and years and years, shortly after their invention. And the reason why quantum computing is so successful is because everybody imagines, or many people imagine, how it can help them, and they go use these machines that aren't doing that much yet to solve problems, but they can already think and use them. I've been incredibly interested in doing the same thing for those of us that do sensors, of making that technology available in some ways over the cloud, so that people can begin to grasp what this technology can do in their own context. I think we're not quite ready for that to happen, but I do think that later down the line, you will begin to see that, because this stuff is hard to do. It's sometimes even harder to imagine how it can help you. And a really critical issue for the nation, not just for the companies, to play a key role in the uptake of quantum sensing as well as quantum computing.
Will some of the tools and platforms be made available to allow engineering community to collaborate and provide feedback and input?
Okay, so you're referring to any for example, modeling tools that are used to model quantum sensors. And yes, I think that is well, okay, so I think there's the easier answer from someone training students in academia is that it is always our intention when we develop something to be able to write that up in a publication and disseminate to the community. And actually, if it involves modeling, then actually the best way really to have your model be useful is to actually put it on GitHub and actually have it be downloadable. So I think this question is a lot easier to answer, from the perspective of academia, which is that we do want to make everything open and usable, because that's also provides a good way to actually improve your model or your software. Or maybe another example is that actually our group also benefits when we're building up our microscope for measuring some of these quantum systems. It requires a certain amount of controlling hardware and hardware-software interface setting up, and we're basically using open source codes, in particular QD, that's available, from the web, from GitHub.
We have time for one last question, right? Yeah.
Hi, everyone. Thank you for your insight. Jacques Philoctet, you've made a great point around the technical challenges and the price performance barriers. I'd love to go back to that. What do you see are the main primary performance price barriers for quantum sensing technology to be more widely adopted in the commercial markets? And is that a path through collaboration with the public, private sector, or perhaps international partnerships and collaborations?
I can take a stab. So it really, the way I see it is that if you look at and I'll just stick to what I know, or what I know something about, which is the PNT application. So with the PNT application, you need to find that there's somebody with the problem severe enough that they're willing to adopt the solution. You can define it, and you can define how your quantum sensor is like giving them value, right? So in our case, you can go 2 to 100, depending on if you have a good day or bad day, sometimes twice as well, sometimes 100 times better with our system than without it. So does that help somebody or not? Yes, no. That's like one of the things. Then how much does it help them, and what equipment do they have currently? And how expensive is their platform? As an example, if a drone costs $1,000 and it needs an alternative PNT solution, then of course your solution has to be a fraction of that. If an aircraft costs $100 million, then you have a different space. And so my answer would be it partly depends on which market you've targeted. I think that for these large capital assets, which would be things like commercial aircraft or military aircraft or ships, where they're worth quite a lot of money and they have historically spent a significant amount of money on PNT technology, classical PNT technology, then you can make a reasoned estimate about, well, where does the price need to fall? So then I think your question is, well, what's blocking us from meeting that? I would say that if we want to have something that's truly globally scalable, a scalable manufacturing where the price can get into single-digit thousands for quantum sensors, or even into the hundreds, would unlock a huge amount of opportunity relative to where we are today. And there's many things that are in the way.
Okay. Right. Well, thank you. I think we're just about to run out of time. So with that, let's thank all of the panelists.